condensations you have come across in aliphatic electrophilic substitutions. So before this, you have come across collision condensation. So what is the common feature? Among all of these, we are exploiting the keto-enol tautomerism. So keto-enol tautomers undergo deprotonation, generating a enolate. So this is a common feature, generating the enolate. Enolate further reacts with another ester, another aldehyde, a ketone, an anhydride, or acid halide, etc. So these are the variable positions. First of all, it may be an ester, it may be a aldehyde, it may be a ketone or any other carbonyl functional group, which first is tautomerized with enol form. Enol reacts with the presence of a base, which is normally alkoxidine. So which picks up a proton from here, generates an enolate. Enolate further undergo addition to a carbonyl system. So this is the overall story. So you have come across three different kinds. In collision condensation, it is the normally ester, which is the nucleophile. The enolate is the nucleophile, and another ester or the same ester is the recipient, electron deficient entity, where a electrophilic addition in fact takes place. So this is the replacement and resulting in the presence of 1,3-dicarbonyl compounds. And in collision Schmidt, we are having the ester. Ester is the same entity, but recipient is our electron deficient entity is in fact ketone. In previous collision condensation, you have an ester here as well. This is the major difference between collision and collision Schmidt condensation. Similarly, you have come across Perkins condensation. Our starting material are carbonyl system which undergo keto-enol tautomerism is an anhydride. It is not an ester right now. So this ester further undergo this mechanism you have already come across, coupling with an aldehyde to result in the formation of this system, which is a alpha beta unsaturated ketone, carboxylic acid. This is the difference in outcome. In previous, you have seen it results in the formation of a alpha beta unsaturated esters. In first case, collision condensation, it results 1,3-dicarbonyl compounds. So these are the three different condensations, starting with a different substrate, coupling with a different reagent to result in the formation of a different outcome. So today we are going to start another important condensation, which is called Reformatsky reaction. Reformatsky is one of the scientists who was working on the organometallics. So organometallics are such transition metal complexes in which we are having a metal carbon bond. And Reformatsky was working on zinc metal. So he was working on organo-zinc compounds. So what is Reformatsky reaction? Reformatsky reaction basically started with the ester again. The same you have come across for collision and collision Schmidt condensation. First of all, he reacted this with chlorine or bromine or iodine in the presence of base. So when we react, this is very simple. When we are going to react this substrate, ester is not substrate for a Reformatsky reaction. Alpha halo ester is the substrate. Now how he synthesized this alpha halo ester? First, if we are reacting this with a base, the base shall pick up a proton from enol form of the generating an enolate. Enolate is when reacted with an electrophile. Here electrophile is chlorine molecule, bromine molecule, or iodine molecule. So it's substitute one of the X leaves with electron pair, and this carbon donate one electron pair to this X. X may be chlorine, it may be bromine, it may be iodine. So we shall get a substitution at this place. No doubt it shall cause racemization because X can be approached above the plane as well as behind the plane. So it shall be a mixture of both enantiomers in exactly same ratio. That's why it has been highlighted in a racemic modification. So anyhow, this is the substrate. You can see this is different substrate from collision and collision Schmidt condensation. Now, once this ester, now we are not going to react this with a base. What is done? It is reacted with a zinc metal. Once it is reacted with zinc metal, now what is important aspect to look at this carbon? X. It is chlorine, bromine, or iodine. All these three are more electronegative than carbon. So we are having a partial positive charge on carbon and partial negative charge on X. Either this is chlorine, bromine, or iodine. So this carbon is electron deficient in this system, but when we react this with zinc, zinc is a pure metal. This is called activated zinc. So zinc basically lose an electron pair which inserts between this carbon and this X bond. This is called oxidative addition. Now why this is called it is addition? Because the zinc metal has been added between this carbon and X bond. You see, this bond is between carbon and halogen. But if zinc inserts in between these two, so we are getting this carbon bonded with zinc and zinc bonded with X. This is called insertion. But this insertion or this addition is called oxidative addition. Addition no doubt taking place between carbon X bond, but it causes an oxidation. Oxidation of what? Oxidation of metal. So when we are reacting this with zinc, zinc is in zero state. It has zero oxidation state. But when it results in the formation of this product, you see the same carbon, this one, is not bonded with X. It is bonded with zinc. Zinc is bonded with X, right? Now in this case, zinc bonded with carbon. If you have any metal bonded with carbon, all metals has electronegativity less than carbon. Carbon has electronegativity 2.5 Pauling's unit. Whereas if it is bonded with any metal, not particularly zinc, any metal, so it's all metal have maximum electronegativity is 1.3 or 1.4 in between them. No metal has electronegativity greater than 1.4. All metals has electronegativity less than that. So if it is less and they are bonded with carbon, all metals shall be positively charged and carbon shall be negatively charged. Now you see here enolate is not generated because in previous example we have a negative charge on this carbon, carbonyl. So that carbonyl was going to react. But here it is entirely different. It is a carbon zinc bond. Organo zinc this is commonly called. So this is the first reaction reported by Reformatsky. So Reformatsky first of all reported this reaction starting from alpha halo esters. He reacted that with activated zinc, which causes oxidative addition, which results in the formation of an organozinc compound. This organozinc was further reacted with a ketone. You see, this carbon, which is carbon bonded with zinc, so this carbon is negatively charged. What is done? This carbon, which is electron deficient in this case, is being converted into carbon with negative charge. So there is a reverse in polarity. Here this carbon is electron deficient, but when it is bonded with zinc, this carbon is electron rich. So electron deficient carbon is converted into electron rich carbon. Now this carbon transfers electron density here. This zinc leaves without electron pair. So it makes, because this electron pair shall transfer on oxygen. Oxygen is negatively charged. So this zinc shall sit with this oxygen. You see, here I have presented carbonyl carbon, right? So this oxygen is bonded with zinc. When we shall work up means when we shall add acid to this. So the acid anion shall take the zinc off and shall get a negative charge here. And the H positive ion shall protonating this one, resulting in the formation of this beta hydroxy esters. Now you see this is alpha carbon, this is beta carbon. At beta we have a hydroxyl OH. Now if we heat this molecule in the presence of acid, and so this shall be protonated, and one hydrogen from here and OH from protonated OH from here shall leave, resulting a carbon carbon double bond. This is if we desire. So it shall produce another, in fact, alpha beta unsaturated ester, which is the outcome of Claisen-Schmidt condensation already. So, but normally in Reformatsky reaction, we don't leave this molecule. So, but if we desire, we can remove this OH from here, protonating this one, and a hydrogen from here shall leave without electron pair, and this shall leave with electron pair. So this is commonly called Reformatsky reaction. Reformatsky is the name of the scientist who first converted ester into alpha haloester, and then reacted that with activated zinc. Activated zinc inserts between this carbon X bond like this. Now making this carbon which is electron deficient in structure number 1, and in structure number 3 this is electron rich. This is the transformation or difference we have converted in a single step the electron deficient carbon into electron rich. Now this is not a carbanion. If it is simple carbanion, this is a simple Schmidt uh, Claisen-Schmidt condensation. All right. Now negative charge on carbon is generated by a different way. This is what is being done, and we are successful to generate beta hydroxy esters, and a new carbon-carbon bond has been generated between a ketone and a simple ester. This is what is called Reformatsky reaction. Now let's see proceed further. Darzon's reaction. In Darzon's reaction, this reaction is entirely different. Look at the substrate. We are having alpha halo esters. Alpha halo esters are being used and reacted with the ketone. These are the same substrate you have come across in previous reaction. But here, this X is good living group. Not necessarily it should be halogen. It may be any good living group. It may be tosylate, it may be brosylate, it may be nosylate, triflate, acetate, or any other entity. Good living group. So we are reacting this with alkoxidine, but it is not reacted with zinc. So we are not converting the alpha halo ester into organozinc compound. So it is not going to be converted. This structure number 1, we are having X is a good living group. It can be any good living group. And then it is reacted with an alkoxide, and it look at the product which is we are obtaining structure number 2. It is a alpha beta epoxy group. This is a epoxy group to a ester. You see, this is entirely different from previous finding. This is a different type of substrate. Now how this is being produced? First of all, look at here. The structure number 1, it undergo tautomerization. If it undergo tautomerization, it shall generate a enolate. All right. So this enolate, this hydrogen is picked up by this base. When it is picked up by this base, so it shall transfer this electronic density here between carbon oxygen double bond, and this pi electronic density shall transfer to this carbonyl compound which is a keystone. So This is the same reaction almost you have seen in previous, very similar. This carbon is transferring electronic then, but mechanism is different. Here we are not generating any inolate, but here we are generating an inolate. This is the difference. So in previous we are using an organometallic. This is an organometallic compound. This is not an organometallic. This is a simple enolate. So simple enolate results in the carbon oxygen double bond just like this, and transferring this pi electronic density to this carbonyl carbon, which undergoes the generation of a new carbon-carbon bond between alpha carbon of an ester and a carbonyl carbon of a ketone. Now what happens is very interesting in this case. Just look at here. This arrow is not right. This is need replacement. This X group leaves. X, because we have defined this is a good living group. This X group leaves. At the same time, this oxygen transfers electronic density to this carbon, not to this carbon. It is not going to transfer because this carbon is not going to be electron deficient. This carbon is electron deficient because this X is leaving. So this just we need the correction of this. I shall make it. You shall also try to make these changes. This oxygen transfers electronic density to this carbon. It is already making a bond with this carbon. When it is making a carbon bond with this carbon, it shall form a three-membered ring. If you remember, this is called epoxide functional group, three-membered ring with oxygen. And this you have come across in epoxidation or reaction of olefins with MCPBA, if you remember. This is the same entity. And when we ring open this, you have already come across this in addition, where epoxy group reaction of an olefin with MCPBA, whenever we do, we got an epoxy group. This epoxy group is once protonated. So it is protonated. A water molecule can approach from this side, or a water molecule can approach from this side. There are two possibilities. So it shall generate both hydroxyl shall be opposite. If this hydroxyl is above the plane, this hydroxyl shall be behind the plane. And in this case, if this hydroxyl is behind the plane, this hydroxyl shall be above the plane. These are the two variation in this. Now you can see these two compounds are having configuration totally opposite to them. So these two compounds are in fact, these two compounds 3A and 3B, they are enantiomers of each other. So this is the, in fact, variation among both of these two structures. These structure number 3A and 3B, they are enantiomer, pure enantiomers of each other, originating from the structure number 2. So this is the major difference between the previous and this one. You can see entirely different products have been obtained. Epoxy group you haven't observed before. So in previous reaction, we are using a alpha halo ester reacting with a ketone. This carbon is electron rich, transferring electronic density to this carbonyl carbon. And in next one, you have come across, we are just totally opposite, in which we are having a negative charge on alpha carbon, but this is okay. So in Darzan's condensation, this is the substrate number 1, which is entirely different, and it is going to condense with the Darzan's condensation. We are reacting the structure number 4 with a ketone, resulting in the formation of a new carbon-carbon bond, and this good living group X leaves, and the oxygen which is present here transfers to this carbon, resulting in the formation of an epoxide. This epoxy group, with the help of this uh, protonated water. Mean we have a traces of H positive ion in water. It undergoes the elimination of this group. First of all, it protonates this epoxy group because three-membered ring are highly unstable. That's why water act as a nucleophile approaching this carbon or that carbon. You see, whenever it approaches, it shall approach totally from opposite direction. So resulting in the formation of two hydroxyl group totally opposite to each other. These two hydroxyl may be opposite like this may be opposite like this. Both hydroxyl above the plane or both hydroxyl behind the plane, they are not possible in fact. So this is the reason that we are having in between these two entities. Uh, Structure number 3A and 3B are totally formed in fact. So these two structures are in fact having two hydroxyl group pointing opposite to each. So structure number 3A and 3B, both of these are enantiomers of each in fact. So this is the Darson's condensation or Darson's reaction in which we are getting the alpha beta dihydroxyesters, which is entirely different from the previous outcome. You see, in case of Reformatsky reaction, we are having just beta hydroxy, not alpha. There is no hydroxy at alpha position, right? And in Perkin, you have see we have ending with a alpha beta unsaturated. For Claisen Schmidt, we are again ended with a alpha beta unsaturated. For Claisen, we are ending with 1,3 dicarbonyl system. Now you can see we have seen 5 different types of the condensation, and in all of these condensation reactions, the stereochemical outcome or the structure of the compounds are different. So we shall continue this. The first session is about to end. So we shall log in instantly, but we shall have a 5 minutes break.